Hello all. In the last session, we have seen one lab experiment where we have developed a simple machine learning model which will work on linear regression, right? So we have used Boston dataset, house price prediction dataset for working on with simple linear regression model. So today in this session, I would like to focus on applying various regression models on a given dataset and find the proper model for prediction with minimal errors. That is, we are going to work on the same Boston dataset, but not just with simple linear regression. We'll also apply multiple linear regression and also polynomial regression and see or compare which machine learning model, whether it is simple, multiple or polynomial, works best on this particular given data set. Okay, so for working on with this particular experiment, we will first import the libraries and load the data set from the URL. Okay, so I have imported these libraries, NumPy for numerical operations, Pandas for loading the data set, and for train test splitting linear regression model for importing polynomial features, I'll import sklearn. Okay, so if you want to go for train test splitting from sklearn.model selection, we import train test split, and the linear regression model is imported from sklearn.linear underscore model. For working on with polynomial regression, we need to extract the polynomial features which I am taking from sklearn.preprocessing, and I also want to compare the performance of three different models, hence I have to work with the metrics. Okay, so in the last session we have seen about mean square error, mean absolute error. So in this session I would also want to include R square error. Okay, R square. Okay, so from sklearn.metrics I'll import mean squared error function, mean absolute error function, R2 score function. Okay, and for simple visualization I'm also importing matplotlib and seaborn. Okay, so if you want to work with Jupyter, you have to import matplotlib.inline. Okay, so the same data set that we have used in the last session, I'm using the same thing from the GitHub. From Selva86 account, I am just importing Boston housing data set. I am reading that particular URL and then loading that particular, reading that URL from pd.read_csv. Okay, and then I want to display first few rows of the data set like what we have seen. So we have different parameters, and in the last session we have taken RM to be the input variable and medieval price to be the output variable. So in today's session also the output variable would remain same, but the input variable changes. When you're going for simple linear regression, we have only one input variable for which we will take RM, but when you go for multiple linear regression, we have multiple features taken into consideration for calculating medieval, that is the output target variable, hence we will consider all the features. So let's see how do we do that. So before we actually develop the model, we have to prepare the data. So for preparing the data, what I am doing here is I want to separate my input features from output features. My output variable that I want to take is this particular column. Okay, so median house price. Okay, MEDV is nothing but the output variable, hence I want to drop that from X. So now X will have all the features except MEDV. Okay, that is the median house price, and that I am taking it as my output variable. This is how I prepare my data. X currently is all the features except MEDV, and that MEDV I am taking it into my output variable Y. After that I try to train and test split the data. As you can observe here, the test size is 0.2, which means that 20% of the data is taken for testing. That is, training data will have 80%. Okay. Now once I am done with importing the libraries and prepare the data set, I will now work on with developing simple linear regression model. So we'll work on three models and compare the performance analysis of the three models. Okay. So first let's work on with simple linear regression. Okay. So unlike X where I had all the features, in simple linear regression I want only X to be one input feature. So for which I take X train and Y train, that is X train Y train I want only RM, that is I am selecting a single feature as input for simple linear regression algorithm, and that is stored in your X train underscore RM, X test underscore RM. After I take this, I'll apply or I'll develop a simple linear regression model. Here when you're fitting the model, first load the model simple linear regression, and when you fit the model, instead of X train and Y train that you have normally taken, we have to load X train underscore RM, Y train underscore Y train. Okay. Now I want to predict the results based on this RM value only. Okay. Now after that, for evaluation, I want to evaluate mean square error. I also want to evaluate mean absolute error. I also want to evaluate R2 score. Okay. I want to print what is the RM value for mean square error, for mean absolute error and R square error. As you can see here, the output, the mean square error value is 46, mean absolute error is 4.48 and R square value is 0.37. Okay. So this is the result of the evaluation that I have taken. Okay. So what did I do here? Instead of working on with the entire data set of X with all input features, as it is simple linear regression, I want to choose only one input parameter, and that input parameter is RM. I have imported the function linear regression, which I've already imported from sklearn. I'm just using that, and I'm fitting extrain data into this particular function, and I'm trying to predict the same for X test. Okay, and I'm evaluating mean square error, mean absolute error and R square values. Okay, now I want to plot the predictions. I am plotting the as you can see, the scatter plot for X test and Y test, the line plot for prediction. Okay, for Y test original values, I want scatter plot, the line for the predicted values, and I want to label them. Okay. So when you observe this particular thing, average number of rooms, RM is nothing but my input variable, and the output variable is nothing but MEDV, which is nothing but the house price. Okay. So dots represent actual, line represents your predictions. As you can see, this is a simple linear regression line which is comparing the average number of rooms and predicting the house price. Okay. Now we'll see how do we implement multiple linear regression. Now here in the previous case, when I talk about simple linear regression, I have change in X. I want only one input variable to be taken into X. For that reason, I've recalled xtrain underscore linear regression model again, RM again. Okay, as you can see here, I have imported xtrain xtest again because I want to take only one feature. But in case of multiple linear regression, I want to take xtrain ytrain as it is, that is with all features. Okay, so I am directly importing linear regression algorithm. See, as I told you, the function linear regression is same for simple or multiple. Okay, the parameters that we pass in xtrain and xtest would be different. In simple linear regression, xtrain and xtest will have only one feature. In multiple linear regression, we have multiple features, but the function linear regression is same. Okay, so multiple LR is equal to linear regression. I am trying to fit xtrain and ytrain, and I am trying to evaluate mean square error, mean absolute error and R2 score. The code would be the same. Okay, now I want to print the same. For mean square error, it is 24.29, absolute error it is 3.19, R square score is 0.67. This is all about multiple linear regression. Okay, now I want to visualize the same thing. I want scatter plot for predictions, line plot for the tested values. Okay, now when you can say this, see actual prices. Okay, I am considering all the input variables. Depending on that, I am going for predicted price. Okay, now this is your multiple linear regression line which will give you the graph between actual prices and predicted prices. I don't have one input variable here. I have multiple variables. That is the reason I am plotting actual prices versus predicted prices. Okay, and then we'll see how do we implement polynomial regression. Okay, we have to use all features, and here I am taking degree as 2. You can change your degree and check for different variations. Okay, now with polynomial degree as 2, first of all I have to import the function polynomial features with degree is equal to 2 as a parameter which is in passing, and then I am trying to fit the model with respect to xtrain and xtest. Okay, so fit underscore transform with respect to xtrain and try to predict with respect to xtest. Okay, after I import the polynomial features, I again use the model, same linear regression model. But when you see this linear regression model, I am trying to recall x polynomial train which had these polynomial features included. Okay, so this part of reading x comma y dot fit x comma y would be changed in polynomial linear regression, wherein we will read polynomial features first and then apply that onto the train data and test data of x. Okay, so first apply the polynomial features onto train data, test data, and fit these train data and test data into the linear regression model. Okay, so just remember, in simple linear regression, xtrain, xtest with respect to one variable, fit that into linear regression model. In multiple linear regression, x is equal to all features, y is 1, fit that into the linear regression model. When I talk about polynomial regression, import the polynomial features first, apply the polynomial features applied x train and x test into the fitted model. Okay. So here in poly lr dot fit, I am applying x poly train and y train. Okay. Now same simple evaluation again, mean square error, mean absolute error and r square error. So here as you can see, the mean square error is 14.57, mean absolute error is 2.64, r square is 0.80. Okay. So what did we do so far? So we have used a Boston housing data set. We tried to apply simple linear regression by taking RM as input and MEDV as output on the simple linear regression algorithm, and we have calculated MSE, MAE, R square. First one. Second algorithm, we tried to implement the same Boston housing data set with multiple features as X and tried to predict MSE, MAE and R square. In the third algorithm, I have tried to implement polynomial regression with degree 2, and then I also tried to predict MSE, MAE and R square. Okay. Now the next question is, how do we visualize polynomial regression? The same thing, actual prices with the predicted prices. Okay. So scatter plot for predicted poly, and for test results I am going for line plot, and I am trying to plot actual versus predicted prices. Okay. Now this is the summary of results of all the three algorithms. Okay. So summary of model performance, I am trying to print MSE, MAE and R square score of all the three models. MSE 46.14, MAE 4.48, R square is 0.37. Here MSE is gradually reduced, the error is gradually reduced from 46 to 24. This is because you have considered predicting the output based on so many features but not just on one feature. Because when I talk about a house price prediction, usually in general in real time, when I want to buy a house, I just don't look at two bedroom or 3 bedroom. I also look at the locality, because the house, the 2 BHK price in Himayat Nagar is different from 2 BHK price in some Rangareddy district, or 2 BHK price in Jubilee Hills, or 2 BHK price in Secunderabad. Depending upon the locality, depending upon the size of the bedroom, and 2 BHK is not available in the same size always, right? So we have different square feet sizes available. So the output would be more accurate when you consider more features. Hence, as you can see, in case of multiple linear regression where I have included all the features, my error is gradually reduced because the predictions are more proper. Okay. And when you go for polynomial regression, again the error is still gradually reduced. Okay. So this is how you can compare MSE values, MAE values and R square values of simple linear regression, multiple linear regression and polynomial regression. Okay. Now which model is better? Okay. The question is, what is our experiment all about? Our experiment is all about apply different different regression models onto the same data set and compare the performance of different models and find the model with the minimal error, right? So when I try to compare the models, we see that simple linear regression has the worst performance because it has only one feature, that is RM. So it fails to capture the complex data, hence the error is more. The error is around 50%, that is 46.14. Okay. Now when I talk about multiple linear regression, it will perform likely better than simple, since it uses all features as I told you, allowing it to learn more complex patterns in the data. It should generally have lower MSE, lower MAE and higher R square. R square value should be higher because it is squared, okay, than simple linear regression. When I talk about polynomial regression, this is the best for this particular data set in terms of MSE and R square if the relationship between the features and target is non-linear. Okay. However, polynomial regression might also overfit the data if the degree is too high. Okay. So overfitting problem occurs if you go for more number of polynomial features. Hence, for that reason, we have considered only degree to be 2. Okay. So which could lead to the model that performs well on the training data but poorly on the testing data. So when it happens, we often go for cross validation to check if the overfitting model can be resolved or not. Okay. So this is all about generalization that we have discussed in the last session. Okay. So here the conclusion is the best model when we talk about MSE, MAE and R square value or generalized model, we say that a model which has lowest MSE and MAE and the highest R square values is said to be a generalized model. When I say generalized model, the model that does not overfit and performs well on both training data and test data. Okay, so for practical purposes, if the R square is significantly higher for polynomial regression and the MSE is low, polynomial regression might be the best solution for this particular data set. However, if you have overfitting occurs, you can go for multiple linear regression. Okay, so if you find polynomial regression is usually the best for this particular data set, but if you find that overfitting problem is there, and if you cannot overcome that by cross validation, you can go with multiple linear regression as the best model. Okay, so this is how we apply different regression models onto the same data set and compare the performance evaluation. Thank you.